Okay. So today I have brought with me a small device which you can also make. I mean, I am just trying to make you understand the gas processes or the four strokes of the engine, or the four processes of the engine, the thermodynamic processes of the engine, and that is what we would like to try to understand with this simple piston cylinder. This is a normal syringe which I have bought, and instead of one let's say outlet, I have just made another small piece here which I have added here. So we can mimic this as an inlet valve and an exhaust valve. Okay. So what we are let us discuss this with respect to a 4-stroke engine itself. So naturally I told you that there are four different strokes. So this at this position the piston is called at the TDC, that means the top dead center or the top center. Okay, so this is called as the top center of the piston motion. When the piston comes at the very bottom, it is called as the bottom dead center or the bottom center. Okay, the bottom center of the position. So the piston reciprocates between the top center and the bottom center. Okay, so piston reciprocates like that, and naturally it is connected to a connecting rod and the crankshaft, so which is not available here to show you, but that is what is happening here. So it is connected, so it is going up and down, reciprocating motion like that, and then there is a connecting rod, and then there is a so this you can mimic like a piston rod. This looks like a piston rod, and then there is a connecting rod and the crankshaft which is rotating. So now with this particular syringe arrangement, let us try to understand the strokes. Okay. So the first thing which you have to do is you have to take in either a mixture, that is a charge, that is air and fuel mixture, like in a typical petrol engine there is a mixture of petrol and air. Okay, how much petrol, how much air, how do you make that mixture, we will discuss that in a later course, but let us say a mixture of petrol vapor and air is available, and we will discuss that with respect to a petrol engine, let us say. Okay. So when you are sucking in, naturally if this one we call as the inlet port. Okay, if this one is called as the inlet port and this one is the larger one is the exhaust port, let us say, then what will happen is when I have to suck this charge inside, I need to close the exhaust valve. Okay, so exhaust valve is closed and my piston is going from the top dead center to the bottom dead center, and in the process it is sucking air fuel mixture from this port or from this valve. Okay, this valve will be open and air fuel mixture will go in. Okay, now once it goes in, now I want to compress it. That means I want to, because eventually I want to raise the pressure and temperature of this system, because my thermodynamic efficiency will depend on how much maximum temperature I am able to reach. Okay, in this, so the source temperature has to be increased. So I don't want to burn it, I don't want to burn this fuel right now, because if I burn right now, the temperature, the pressure is very low. Okay, it is almost like atmospheric pressure right now. So the temperature will also be very low. But if I increase the pressure, naturally the temperature in any case will go up of this particular mixture. Okay, and then after that when I add heat to it, the pressure and temperature will further rise. Okay, and I would get the maximum source temperature, or I will try to get a very high source temperature, because my heat engine efficiency depends on how maximum I can go in this particular compression chamber, in combustion chamber. So I have completed the suction stroke, the charge is inside, the inlet valve was open, and now I want to close both the valves. So I am going to close both the valves now. Okay, both the valves need to be closed because I want to now compress, and now work has to be done. You can see I have to push very hard, and I am able to push only up to this point. Okay, so now it is high pressure. You can see it is high pressure. Okay, it is high pressure, and naturally the temperature has also gone up. Okay, how much it has gone up, it depends on how this process was done. So we can either compress it. If I compress it extremely slowly, if I do it very very slowly, and I just wait, I just do it very quasi steady state, I just compress a little bit more and then wait again, I compress and again wait. So what will happen, whatever temperature rise has taken place inside, I am allowing that temperature rise to equilibrate with the atmosphere. So it is essentially like a isothermal process. So this is, if I do it very, very slowly, okay, or if I am cooling this very rapidly to the ambient temperature, then what will happen? The air inside or the air fuel mixture inside will always be very close to the ambient temperature. So that is called, let us say the wall is very, very conducting and I am blowing air like that on the top, and I am trying to cool this as I am compressing. So as I keep on compressing very slowly, extremely slowly, if I do it, then this particular control volume, the charge in the control volume will get compressed. However, the temperature of that particular charge will be nearly equal to the ambient temperature. So this will be called as isothermal compression. Now suppose if I have an insulating material around this cylinder and I do not allow any heat to go out, okay, I make it completely adiabatic, okay. So you can have, I can still compress it, but I am not allowing any heat because the temperature is rising as I am compressing. So I am not allowing any heat, okay, from the inside of this cylinder to go out. So we have seen two processes. One is a quasi steady process, very slow, with full heat transfer taking place. I am allowing all this heat which is generated inside going out. That is called as isothermal compression. But if I insulate it, I do not allow the heat to go out, then the compression will be called as an adiabatic compression. Okay. So let us make two small diagrams here and try to understand this process. So in the, let us say the first one was an intake, stroke or inlet stroke, okay, and if I put, let us say, inlet valve and exhaust valve, okay. So in the inlet stroke, the inlet valve was open and the exhaust valve was closed, okay. So we went from the top dead center, this was open, and we went down and charge came in, okay. So this was stroke number 1, okay. Now we start the compression. That means now the piston is going up, and mind you, you have to do work against the system. That means the engine has to do work. So the energy which was stored in the flywheel, okay, is now being used to push this piston up. So you have to actually do work against on the system, and therefore this particular gas is getting compressed. And as I said, this compression we can do it. So this is inlet, this is exhaust, the piston is going upwards, okay, the piston is going upwards, both are closed, this is also closed, this is also closed, so closed, and the pressure and temperature is going up. Now you can do it isothermally, as I said, that means there is a lot of heat transfer which is taking place from here. So as you are compressing, the temperature is almost equal to the T ambient, okay. Or you can do it adiabatically, that means you have the piston like that, these are both closed, and then you have an insulating material here, you have everything is insulated, okay. You don't allow any heat to go out of this. So this compression, so this is called as isothermal compression, and in the second case it will be called as adiabatic compression. Okay. Now, so these two are the compression, both valves are closed, okay. So this is closed and this is also closed. Now once the piston comes up, okay, there is a finite volume which is remaining here, which is the combustion chamber, because now we have to ignite the fuel. Now if it is a spark plug, that means if you have a petrol engine, you will typically have a spark plug here and it will ignite. And as I told you in my previous lecture, that the petrol engine is a rapid burning engine, that means the fuel burns very rapidly. Okay. So all the heat which comes in very quickly. Okay. So then you will have a spark, then event of the spark will occur here. Okay. There will be spark, of course this will remain closed, this will remain closed. Okay. The piston would have moved upwards. Okay. So the piston is now nearly here. Okay. And there is a spark plug here. Okay. So let us make here also, there is a spark plug here. Okay. So the piston has really moved upwards, and now this is our combustion chamber. Okay. The combustion is going to take place rapidly here. So all the heat is going to come very suddenly in this process. So what is going to happen, that when this combustion takes place, at that time the spark has occurred, all the heat has come in. So what happens is that since all the heat has come in at this position of the piston, nearly this position of the piston, because it was a very rapidly burning fuel, you can call that as heat addition at constant volume. Mind you, the volume is of the combustion chamber, this is the volume, both valves are closed, spark has just occurred, all the heat has rapidly come in, because it is a petrol engine, it is a rapid fire engine, okay, or rapid burning engine. So all the heat has nearly come in. So the piston did not have the time to go back, okay, or start the downward journey. Even before that, the heat has already come in. Okay. So the heat has come in very rapidly. Okay. So that is why you can call this process as heat addition at constant volume. Now suppose the fuel was a slow burning fuel. Okay. If the fuel was a slow burning fuel, then the burning would have continued, and because of the inertia of the piston, you have already started going down in the downward stroke. Okay. The power has already been started giving, because the heat is coming very slowly, or it is relatively much slower than as compared to a petrol engine. So then what will happen is, as the heat comes in, the enthalpy of the combustion comes in, the piston already starts going down, okay, because of the push which is created by the gas, okay, and the pressure inside is more or less constant. You can idealize it as a constant pressure process. That means as the gas is expanding because of the heat which has come in, it is pushing the piston, and in that process it is trying to maintain a pressure inside, okay, which is the pressure inside to be constant. Okay. So in a petrol engine, heat addition, typically you can idealize it. You need a model to now work on our analysis. So we can idealize it. Okay. What happens in reality is slightly different than this. We will look at that reality a little later on. But for a petrol engine, which is a rapid let us say burning fuel, the heat addition can be considered as soon as the piston comes up, the spark occurs, and very quickly all the heat comes in. So you can call it that this volume does not change actually, and therefore you can say it is heat addition at constant volume. In contrast, if you have a slow burning fuel, then what happens is that the burning continues, because the piston now wants to go down. Okay. And in that process, the heat is coming in, the burning is taking place, it is slightly slower than the petrol one, okay, and therefore the piston has already started delivering power and the heat is still coming in. So the heat will continue, the piston has started going back, and therefore you can idealize it as heat addition at constant pressure. Okay. So as the piston keeps moving down in a diesel engine, the pressure which is inside the combustion chamber tends to remain constant. In reality, of course, it can never remain constant, because there is heat addition is also taking place and the piston is also started moving downwards. But for thermodynamic analysis, we can idealize it as heat addition at constant pressure. We will study the real cycle also, that means how in reality the combustion takes place and what is the dynamics, that small microseconds which are available for combustion in petrol engine and diesel engine, how exactly combustion takes place, that also we will study. But for an ideal processes, you can consider a fast burning fuel as heat addition at constant volume, and a slow burning fuel or a typically slow burning fuel as heat addition at constant pressure. So essentially we have the power stroke which has started, okay, and in the power stroke also naturally this has to remain closed and this has to remain closed, okay, both the valves have to remain closed, because we don't want to lose any gas. The pressure is high, the temperature is high, we want to make sure that this gas which is at high pressure and high temperature pushes only the piston downwards, so that you can get maximum work out of it at this level, okay. And therefore the power stroke you will have both the closed, and then what happens is that all the gases have burnt now and the piston is down, and now what is remaining inside is burnt gases. There are burnt gases inside now. So the fuel has oxidized, you have formed carbon dioxide, hydrogen, water or steam. If the fuel has not burnt completely, then there may be carbon monoxide inside. There may also be some remaining fuel also inside. There may be other compounds depending on the temperature of operation. There may be nitrogen oxides, there may be sulfur dioxides, there may be different other compounds which got oxidized in the process or partially oxidized in the process, and therefore they will be inside this particular chamber. Now we want to get rid of it, of course, okay, and therefore because we want to start the next stroke, okay. And so what will happen now, this is our inlet stroke, the smaller one, the bigger one is the exhaust stroke. So now naturally the exhaust valve has to open, and then the piston goes up and pushes the exhaust out again. And in this exhaust pushing also some amount of work of course has to be done. It is naturally smaller than the compression work, but a small amount of work also has to be done, by which process the piston goes up from the bottom dead center to the top dead center, and it pushes the exhaust gas out, okay. Once that happens, now the exhaust valve can close again and inlet valve can open, okay. And then with that the next stroke, that means after the power you have the exhaust stroke, in which case this is closed, the inlet valve is closed, and then this is open. And once this happens, you can actually go back again to the inlet stroke, okay. So you go back again in this position where the inlet valve now opens and the exhaust valve is closed, and you can get back to the next cycle, that means suction, then compression, then power, and then exhaust, then again suction, again compression, okay. I am not able to compress it completely, as you can see, it's very difficult to push it up. So again power stroke by burning of the fuel, okay, and then again exhaust valve opens and you go up, and then again the cycle repeats. So this is how the 4 strokes of the cycle they operate, and in this process we have done 4 things. Remember, when we were sucking fresh charge inside, we had to do some work. A little work was done to suck the air inside. As you suck your, when we breathe, we have to do work like that. You suck, and then again you compress, you have to do work, okay. So this is the work input to the system, and then the power stroke actually gives you positive work in which the expansion takes place, and you actually get the work done from the system to the environment, which is the outside of this piston. You get work out of this cylinder, and then again to push the exhaust out, we again needed to do some little work, and then heat was added depending on what type of an engine it is. The heat was either added very quickly, so the heat addition was typically at constant volume, and or if it is a slow burning fuel, then typically you can model it as a heat addition at constant pressure. The pressure tends to remain constant till the time all the diesel has burnt up, and the piston has already started its downward journey when the burning is taking place. In this particular condition, all the heat has already come in, and more or less the piston has then started the downward journey to produce the power stroke, for example. Okay. So this is how the engine operation can be simply explained with the help of a small unit which I have here. And then in the next lecture, what we will do, we will try to put these processes onto a thermodynamic diagram. You can make it on a PV diagram, for example, because the pressure, the temperature and the volume of this control, of this particular control volume is changing with all these strokes. Okay. So we should understand what is the pressure, what is the temperature, what is the volume at each stage of these strokes, and then try to analyze it from a thermodynamic point of view, that what will be the efficiency of the system, for example, and how do we understand the transport processes of inlet and exhaust and combustion, etc. in an IC engine.